Today we're going to review how to find the least common denominator and how to solve rational equations. Remember, the least common denominator means that it's going to be the smallest number that both denominators will divide into, not what divides into them, but what they can divide into. It has to be at least as large as your largest numbers. There are a variety of methods for finding the LCD. Oftentimes, if the numbers are pretty small, you can just look at the numbers and know what is going to be the smallest thing they'll both divide into. But if you end up with numbers that are a little bit larger, then you need a method for helping you find that LCD if they're a little difficult to work with. So what I want to show you is a method of prime factorization that will help you. If you know how to get the LCD without it, you do not have to use this method, but when the numbers are large enough you need some help, this will work. Remember that prime numbers are numbers that are divisible only by themselves in 1. So our list of the first few prime numbers, the smallest prime is 2, then you have 3, 5, 7, 11, 13, and so on. If you need to, make you a little help list to remind yourself what the prime numbers are. We want to figure out how to factor 30 using only those prime numbers. So as long as it's an even number, begin by dividing the number by 2. 2 would go into 30 15 times. This is no longer an even number, but I do know that 3, which is the next prime number, will go into 15, and it will go 5 times. That gives me a prime factorization for 30 of 2 times 3 times 5. We can do the same thing for 20. I'm going to save a little space and assume you can do this on your paper yourself. If you write out the prime factorization for 20, you have 2 times 2 times 5. Notice I didn't write it as 4 times 5. That's because 4 is not a prime number. I can only use prime numbers. Now, to find the LCD, I have to use at least one of every different factor that occurs. So if I look at this factorization, I see 2's and 3's and 5's. But I notice that I have 2's in more than one place. 2 is a factor in 30. 2 is also a factor in 20. And what I do is determine where does it occur the most. I have 2 2's in the factorization of 20 compared to only 1 2 in the factorization of 30. So I'm going to keep the 2 2's in the factorization of 20, and I will get rid of the one that's in the list for 30. As if I keep 2 2's, I've already got this one covered. Now remember, I said I have to have one of every different factor, so I'm going to have to keep the 3. And when I get to 5's, I notice it occurs in both places. It's a tie. And when it's a tie, you keep one, you get rid of the other. So I'll keep one of these 5's, I'll get rid of the other. And what I will have left is 2 times 2 times 3 times 5, which is 60. That would be the LCD for 30 and 20. Now, if you look at number 2, these are not just plain numbers. We now have variables involved, and we have more than one term in one of these denominators. That's a binomial. When that occurs, make sure you try to factor first. If anything will factor, you need to do that. So the 5r minus 25 has a common factor of 5. That would give us r minus 5 in parentheses. The 15r to the third, if we use the prime factorization, would be 3 times 5 times r to the third. Same principle as before. I have to use one of every different factor that occurs. So when I'm looking for the LCD, I know I have to keep this 3. I have 5's in both places. So I'll keep one, get rid of the other. Notice I have r to the third on the bottom. I do not have any plain r's on the top. The only place where I see an r is in the parentheses for the binomial. So I have to keep the r to the third and I have to keep the binomial. And that would tell me that my LCD, when I multiply these back together, would be 15 r to the third times r minus 5 in parentheses. If you choose to use distributive property and multiply it out, that's okay, but it's also okay to leave it in factored form. If we go to number 3, what we see is another pair of monomials, but this time there are variables with exponents involved. So we're going to need a little help or a little reminder of what to do when that occurs. The numbers themselves, the 8 and the 6, if I do the prime factorization or if I just look at the numbers and know it, I should determine that the number portion of my LCD is 24. That's the smallest number that both 8 and 6 will divide into evenly. But when I check the variables, what I have to do is take the one that has the highest exponent. Remember, I said you can't ever have an LCD that's smaller than what the largest, at the time I said the largest number is. It can't be any smaller than your largest exponent either whenever you're talking about variables. So if I see I have a's in both places, I know I have to have an a to some power. I'll pick the one with a larger exponent. So 24a squared b squared becomes my LCD if my monomial has both numbers and variables. When you look at number 4, again, I see I've got some factoring I'm going to need to do. And this time, both denominators are trinomials, so I'm going to use that AC method to factor. Number that multiply, or two numbers that multiply to give me 8, add to give me 6 would be 4 and 2. So it's going to multiply to give me t plus 4, t plus 2. My second denominator, t squared plus t minus 12, is going to factor into t plus 4 times t minus 3. If you need a review for factoring, remember you can go back and watch the video on how to review how to factor. Same process, I have to have at least one of each different factor. So since I have t plus 4 in two places, I will keep one and I will get rid of the other. But I also have to keep the t plus 2 and I have to keep the t minus 3. In any order, I need these three parentheses, t plus 4, t plus 2, and t minus 3. And that would be the LCD for those two rational expressions. Now, sometimes we may need to rewrite a fraction with a new denominator. The process for that is pretty simple. If I look at the denominator that I have, the 8n, and I want it to end up being a fraction with a denominator of 24n to the 6th, I am basically asking myself, what would I have to multiply this by to turn it into 24n to the 6th? So if I look at the numbers, 8 times 3 is how I'll get the 24. If I already have n to the first, I need to multiply it times n to the 5th for it to turn into n to the 6th. Now don't forget some of your basic rules of algebra. If I'm trying to multiply a fraction by some value, if I multiply the denominator by something, the only way my fraction can have the same meaning is if I also multiply the numerator by the same thing. Remember, anything divided by itself is equal to 1. As long as I'm multiplying my fraction by something that means 1, then I will have an equivalent fraction. So once I determine that 3n to the 5th is what's needed to get the denominator for what it needs to be, I also multiply the numerator by that, and that would tell me when I multiply straight across, 21m to the 5th would be my new numerator. Same principle for our second example, except we have to factor first in order to find what the factorization looks like. Otherwise, I'm going to have a hard time seeing what is the missing part that I need to multiply by. If I look at this trinomial on the right, don't overlook the fact that you have a common factor of 3. So if I factor that out, I'll have 3 times 4z squared plus 5z plus 1. Again, if you need to review how to factor using the AC method, go back to that video. I'm going to save a little time. And so we will end up factoring this using the AC method, which if you need to review, you go back and look at that lesson on how to factor, and we will have our 3 for our common factor, but 4z squared plus 5z plus 1 will factor into 4z plus 1 times z plus 1. And you can double check, multiply it back out using FOIL or the box to see that it really will equal what our original trinomial was. Now, as I'm looking for that LCD, I need to ask myself, if I already have 3 times z plus 1 in the denominator, then what would I need to multiply by to end up with 3 times 4z plus 1 times z plus 1? Well, the only part I'm missing is the 4z plus 1. And if I multiply the denominator by 4z plus 1, I must also multiply the numerator by 4z plus 1. That would tell me that 8z times 4z plus 1 would be the correct numerator for the new fraction. So that's simply a review of how to get an equivalent denominator. Very helpful if you ever have to add or subtract fractions. But let's go back now to talking about why we need that LCD, and it's because if we are solving equations with rational expressions that are in them, in other words, equations that have fractions, we can eliminate the fractions if we multiply every term by the LCD. So if we look at this example number 6, we have denominators of 5 and 3. It makes it very simple to determine our LCD here. Our LCD will be 15. And if we multiply every term, both sides of the equation, by 15, we will eliminate the fractions. So we multiply the left side by 15, and we multiply the right side by 15. Notice that I'm not multiplying by 15 over 15. The entire fraction gets multiplied by the LCD as a whole number. It's just in the numerator. If you want to think of it as being over 1, so it looks like a fraction times a fraction, then you may write it that way. Now, if I've chosen the LCD correctly, what will happen is my denominator will cancel with part of the LCD. It will divide into it evenly. So 5 goes into 5 once, goes into 15 3 times. That would mean on the left, I have x minus 4 times 3. On the right side, 3 goes into 3 once, goes into 15 5 times, and I will have x plus 2 times 5. Notice no fractions. My denominators both became 1, so I no longer have fractions. Using distributive property, 3x minus 12 on the left would equal 5x plus 10 on the right. I have a simple linear equation to solve. If I move 3x to the right to combine the x terms, I will end up with a negative 12 equals 2x plus 10. Let's move 10 to the left, subtract 10 from each side. I will have 2x on the right, negative 22 on the left. Dividing each side of the equation by 2 to isolate the x gives me x equals negative 11. Now, notice it said we have to check our solutions. So that means if I go back to the original equation, I want to see what happens if I put negative 11 in place of x. On the left side, and you can use a calculator to do this, it's very simple, negative 11 minus 4 would give me negative 15 for my numerator, and negative 15 divided by 5 is a negative 3. So the value of the left side of the equation when x is negative 11 is a negative 3. If I plug in negative 11 on the right, negative 11 plus 2 is negative 9, and negative 9 divided by 3 would give me a value of negative 3. My left side equals the right. Negative 3 equals negative 3. Therefore, x equals negative 11 is a solution. Now, truthfully, what you're primarily going to check for with these rational equations to see that your solution works is, remember from the very first lesson when we worked with rational expressions, we said the one concern we have is we cannot allow our denominator to have a value of 0 because that makes the fraction undefined. So primarily you want to see if the value of x, when you plug it into the original equation, would give a denominator of 0. That wasn't an issue for this equation because we didn't even have a variable in the denominator. So as long as you don't get 0 in the denominator, unless you've made an arithmetic mistake, your value for x should be a solution. If you look at the next example, number 7, we no longer have just numbers in the denominator. In fact, the first two fractions are binomials and need to be factored. So we're going to factor the first denominator into 2 times m plus 2. The second denominator gets multiplied into 3 times m plus 2. So if we rewrite them in factored form, it makes it a little easier for us to identify our LCD. I have the numbers 2, 3, and 9 in each of those denominators. I'm looking for the smallest number they all divide into evenly. It will have to be 18. If I then check the remaining parts of the denominators, I have m plus 2 in 2 of the 3 denominators. It's a tie, so I keep one, I get rid of the other, and 18 times m plus 2 is going to be my LCD. I will now multiply every fraction times 18 times m plus 2, which is the LCD. I'm going to squeeze it in up here at the top just to save a little space. And I will reduce down where I can. So 2 will go into 18 9 times, and those m plus 2's cancel out in the first fraction. What that leaves is the original 8 in the numerator times the 9 for the LCD, and I get 72. If I move to the second fraction, 3 goes into 18 6 times. Again, the m plus 2's will cancel out. That will leave me with 2 times 6, which is 12. For the second fraction, I have 72 plus 12 on the left. Let's clean up the right. 9 will go into 18 2 times. If I multiply back together the remaining pieces, I will have 7 times 2, which is 14, times the m plus 2. And at this point, I'm ready to use the distributive property and clean things up and solve. So on the left, combining 72 and 12, I get 84 is equal to, on the right, I'll have 14m plus 28. If I subtract 28 from both sides, I will have 56 equals 14m. Dividing both sides by 14 will tell me that m equals 4. And if I go back and I look at the original problem, and I can check it in factored form, using 4 in any of the denominators will not create 0 in a denominator. I won't have anything that becomes undefined. Therefore, that should be a solution. We have a little bit of a formatting issue here with problem number 9. This actually belongs over here. So let's look at number 8. And what I want to do is rewrite it, but I notice that the first fraction, the denominator, can be factored. So I'm going to rewrite it in factored form. And I'm going to have a pair of numbers that multiplies to give me -6, adds to give me +5. That should be z plus 6 times z minus 1. My second fraction, the denominator doesn't factor. I can't do anything with it other than just recopy it. Same thing for the fraction on the right. It is z plus 2 over z plus 6. Now when I look for the LCD, notice that this LCD, I only have 2 different factors in all these denominators. I have a z minus 1, a z plus 6. It's not repeated anywhere. So z minus 1 times z plus 6 will be my LCD. And I'm going to multiply every term by that. Z minus 1, z plus 6 for the first, the second, and for the fraction on the right. Okay, if we clean up, first fraction, z plus 6's cancel, z minus 1's cancel, the only thing remaining will be 14. Second fraction, I can cancel out the z minus 1's. That leaves me with the minus 2 that was originally there times the z plus 6 in parentheses. And in the last fraction on the right, z plus 6's cancel. Now, notice the z plus 2. You need to put it in parentheses because the numerator that was there, the entire numerator has to multiply times the z minus 1. This means I've got to be on my toes because this involves either using FOIL or the box to multiply these together. If you leave the parentheses off of z plus 2, you might mistakenly think you just need to use the distributive property with the 2 times the z minus 1. You won't get the right answer. So make sure you realize the entire numerator that's there gets multiplied by the z minus 1. Now, if I simplify using distributive property on the left, I have 14 minus 2z minus 12. Using FOIL or the box on the right, and again, if you need to review that, you can go back to one of the earlier lessons, we would have z squared. The negative 1z plus 2z gives me a plus z for the middle term, minus 2, because positive 2 times negative 1 gives me a negative 2 on the end. I do have some like terms on the left. The 14 minus 12 will give me 2. So 2 minus 2z is equal to z squared plus z minus 2. Now, I have a z squared on the right. That means this is quadratic. It's already positive. Let's move everything else to the right. So we're going to subtract 2 from each side, and we're going to add 2z to each side. When I do that, everything cancels on the left. 0 would equal z squared plus 3z minus 4. When I factor my trinomial on the right, a pair of numbers that would multiply to give me negative 4, add to give me positive 3, would be a positive 4 and a negative 1. So I'm going to have z plus 4 and z minus 1, which if I set each of those factors equal to 0 and solve, I'm going to get two possible solutions for z, a negative 4 or a positive 1. Now remember what we said. We've got two possible solutions here. It could be neither one works, only one works, or they both work. I have to go back and inspect my original problem. And it will be a little easier if you look at the factored forms of your denominator. In this case, if I try to plug in negative 4 to any of these parentheses in the denominator, I don't have a problem. I'm not going to get 0 anywhere. But what happens if I try to plug in 1? Look right here, z minus 1. If I use 1 for z, 1 minus 1 is 0. That's going to create a problem. I cannot use 1, and z equals negative 4 will be my only possible solution. Now, as we look at problem number 9, what I want to do is recopy it, but I'm going to recopy it with the denominators already factored. So 3p is my first numerator. The p squared plus 5p plus 6 will factor into p plus 2 times p plus 3. I have my equal sign. My second fraction, 5p, is the numerator. And to factor that denominator, p squared plus 2p minus 3, means it would factor into p plus 3 times p minus 1. My third fraction, I have a minus 2. And that denominator would factor into p plus 2 times p minus 1. Okay, looking for the LCD, here's what I see. I have p plus 2, it occurs in more than one place, I keep it once. I have p plus 3, it occurs in more than one place, I keep it once, and a p minus 1. So my LCD is all three of those parentheses in any order. And what happens if I multiply each one of these fractions by that LCD, I'm going to get a number of things that will then cancel out. So I'm going to put my p plus 2, p plus 3, p minus 1 for each one of these. And let's cancel what we can. In this first fraction, the p plus 2's will cancel, the p plus 3's will cancel, and that will leave me with 3p times p minus 1 equals, in my second set of fractions, the p plus 3's cancel, the p minus 1's cancel, and that will leave me with the 5p I already had times p plus 2 And in my last fractions, the p plus 2's cancel, the p minus 1's cancel, and that will leave me with minus 2 times p plus 3. All right, looks like a mess, but at least now we have no fractions. We just need to distribute and clean this up. So we'll have 3p squared minus 3p on the left equals 5p squared plus 10p minus 2p minus 6 on the right. If I combine like terms, 3p squared minus 3p on the left would be equal to 5p squared plus 8p minus 6 on the right. Let's move everything to the right side. When we do that, we're going to get 2p squared plus 11p minus 6. And again, I'm going to just tell you what this is when it is factored. You should end up with 2p minus 1 times p plus 6. And if I set each of those parentheses equal to 0 and solve, 2p minus 1 equals 0, or p plus 6 equals 0, then I get two possible solutions for p. It would either be positive 1/2 or negative 6. And I have to go back and double check in the original problem. Using a positive 1/2, I don't see a single denominator that would give me a problem. Using a negative 6, I do not have a problem with the denominator. Those are my two possible solutions.